The next step in our progression of studying molar relationships is to start looking at balanced equations. So we're going to start relating moles of one thing and relating it to moles of another thing in a balanced equation. So let's look at an example equation. You can pick pretty much whatever you want. I went ahead and used a combustion reaction because they tend to be nice and predictable and have some interesting coefficients on here. So in this one, this is the balanced chemical equation for burning propane in air to make carbon dioxide and water vapor. So I can see from this balanced chemical equation that 1 mole of the propane would react with 5 moles of oxygen to make 3 moles of carbon dioxide and 4 moles of water. Following with the calculations that we've done here, where as soon as we start with some other kind of number, things start to feel a little bit different for a while, but we'll make sure that that gets comfortable really soon. So let's ask a question like, how many moles of O2 are needed to completely burn 2.78 moles of C3H8. So in this, we're going to use the same kind of relationship of the elements for each other based on the relationship from that period or from that balanced chemical equation. So this is the same kind of process that we did just a minute ago in our previous video, but we're now relating two different chemicals rather than looking at just one of the elements inside one chemical. But we're going to set it up exactly the same way. Our balanced chemical equation is like a unit conversion factor here. So we're going to take 2.78 moles of C3H8, which is what we are given to start with. And the unit conversion factor that we can see is that 1 mole of C3H8 reacts with 5 moles of O2. So since we want to get rid of moles of C3H8, we'll put that 1 mole of C3H8 on the bottom, and then 5 moles of O2 go on the top. And now we can see that our units are going to cancel out, and we will have moles of O2, which is what the question was asking us for. So when we solve that, pull out your calculator and get a number. You should get 13.9 moles of O2 that would be needed to react with 2.78 moles of C3H8. But we don't just have to look, or we aren't limited to only looking on one side of a balanced chemical equation. We can relate reactants to products through the same kind of relationship. So we can ask as a follow-up question, how many moles of CO2 or H2O are made? And when we answer this question, we can either use the C3H8 to relate to the CO2, or we can use the O2 to relate to the CO2 or the water, depending on what we are doing the calculation. And we should get exactly the same answer. Let's try it out. So pause the video and try starting from 2.78 moles of C3H8 and also from 13.9 moles of O2 and calculate the moles of CO2 and see what happens. All right, if you did the C3H8, we have 1 mole of C3H8 reacting to make 3 moles of CO2. And with the O2, we have 5 moles of O2 that react to produce 3 moles of CO2 from the balanced chemical equation. And both of these should give you the same answer. They certainly did when I calculated it. And I got 8.34 moles of CO2. If you want a little extra practice, go ahead and practice calculating the water as well. I'm going to give you another practice problem here in a minute too, but if you want that extra practice, go ahead. Okay, so the next balanced chemical equation we'll look at, here's another one just for variety. Let's imagine that we've got 6 equivalents of AgI reacting with Fe2CO3, so that'd be iron carbonate to make 2 moles of iron iodide and 3 moles of Ag2CO3. All right, so from the balanced chemical equation again, we can see that 6 moles of the AgI react with 1 mole of Fe2CO3 to make 2 moles of FeI3 and 3 moles of Ag2CO3. So let's say if we react 0.276 moles of Fe2CO3, how many moles AgI are needed to react with it? Set the problem up, go ahead and pause the video and see if you can do this problem without me. All right, if you've got 1.66 moles of AgI, then you've got it. Just in case some of you want me to show you, we have 0.276 moles of Fe2CO3. Now I'm going to use the coefficients from the balanced chemical equation. 1 mole of this iron carbonate relate with 6 moles of AgI. And so when I multiply those through, I get 1.656 moles, but then I rounded it to 3 significant digits because I only had 3 in my iron carbonate number of moles. All right, so we can ask similar kinds of questions. What if we say something like 0.842 moles of iron iodide was produced? So how many moles of silver carbonate also was made? You set this problem up exactly the same way you did. So pause the video and give it a try. Okay, you should have gotten 1.26 moles of silver carbonate. And I did that by setting up 0.842 moles of iron iodide, and then seeing that my balanced chemical equation has 2 moles of FeI3 relating to 3 moles of silver carbonate. Okay, so notice that when we have been doing these mole-to-mole unit conversions, the only thing we need is the balanced chemical equation. That we've been just using this balanced chemical equation to do all of our mole-to-mole relationships. And that's exactly the way we want things to be. because it keeps things really simple. But we don't have to stop there. We've been going grams to grams, but we can also convert to, or excuse me, we've been going moles to moles, but we can also convert into grams too. So let's try another balanced equation. I like to keep some variety going on here. So let's look at the combustion of methane in oxygen. Like all good combustion reactions, it makes carbon dioxide and water. So we might ask something like, how many grams of carbon dioxide will be produced if 8.41 moles of O2 react with methane? All right, so here we have one additional step. Our first step is going to be to do the mole-to-mole relationship. We're going to go from moles of O2 to moles of CO2. We always relate moles of one thing to moles of the other using the balanced chemical equation. There is no other way to do this. So we're going to set up 8.41 moles of O2, and we can see that 2 moles of O2 produce 1 mole of CO2 in the balanced chemical equation. So we can calculate that number of moles. Go ahead and pause my video and calculate it. You should have gotten 4.20 moles of CO2. And our second step now, because we're not totally to the end, we don't have the unit that we are looking for. We've converted from our first material, O2, we've converted into our second material, but now we need grams of that second material. So we're going to use the molecular weight of CO2 to convert moles to grams. So you can see that we're just building on the skills that we've already been practicing. So 4.20 mole of CO2. And now you're going to have to look up the molecular weight. I always set it up 1 mole CO2, and then I know I want grams of CO2. So now pause the video and go to the periodic table and calculate the molecular weight of CO2. All right, so hopefully you've found that it's 44.009 grams carbon dioxide, and I get 185 grams of CO2 being produced. All right, let's try this again, just for a little more practice. So we might ask, how many moles O2 are needed to burn 84.9 grams of methane? So here we're still relating one material to another, but this time we're starting with oxygen and we wanted to relate it to methane. Oh, sorry, we're doing it really the other way around. We have methane. We want to know how much oxygen is needed to burn it. So we're still going to use this same balanced chemical equation, and we're still going to use the same steps, but notice that our steps are reversed. We have grams. We need to go back to moles, so we're going to use the molecular weight. We're going to start with step 2, or what was step 2 in our previous example, and then we're going to go back to what was step 1 in our previous example. All right, so let's do it. Take 84.9 grams of CH4, convert it to moles of CH4, and then convert it to moles of O2. Pause the video, take your time, and give that a try. Okay, you should have found that we need 10.6 moles of O2 in order to do this combustion reaction. So I'm going to go ahead and write these steps out just in case you need it. Our 84.9 grams of CH4 has a molecular weight of 16.043 grams of CH4 to 1 mole of CH4. And then that gives us 5.29 moles of CH4. And this 5.29 moles of CH4, it relates 1 mole of CH4 to 2 moles of O2. And so that's how we get the 10.6 moles of O2. All right, I'm going to give you another example, and I'm not going to tell you how to do it. I want you to just give it a try. So here's our balanced equation. We have 4 iron plus 3 O2, making 2 Fe2O3. So here's our question. If 84.69 grams of O2 react with some iron, how many moles of Fe2O3 are made? Okay, give this a try. Pause the video and then unpause it when you have gotten an answer. All right, welcome back. I hope that you found 1.764 moles of iron oxide. If you didn't, don't give up. I'm going to go ahead and write this out. So strategically, we can see we are starting with O2. We want to go to iron oxide. So our first step is going to be to go to moles. And then, first we're going to go to moles of O2 from grams, and then we'll go to the moles of the Fe2O3. All right, so the other thing that I usually like to do, because it's more condensed, is I'll put all my calculations together in a row. So I'm going to start with 84.69 grams of O2, and then I'll do my first step, which is converting grams into moles. So 1 mole of O2 weighs 31.998 grams of O2. And now I'm going to go directly to that mole to mole step. So I'm going to put my molar relationship right here. 3 moles of O2 go to 2 moles of Fe2O3. And I can do this because I can see that all the units will cancel out. My grams of O2 cancel out with these grams. My moles of O2 cancel out with these moles. And I'm left with moles of iron oxide, which is what I want. So when you do this, you should get 1.764. All right, so far we've gone mole to mole. And we started doing those in our previous video. Now we've also gone grams to moles, and we can go the other direction too. We can go from moles to grams. And we could go back again, because this is moles of A and this is moles of B, moles of A, moles of B. And so grams, this is the direction that we would go. All right, A and B are just 2 different chemicals. So you probably guessed we can actually take this one additional step further. We can start with grams of one thing. We can convert it to moles. We can convert that to moles of some other thing using the balanced equation, and then we can convert that to grams. So we've done all of these individual steps, and of course, either direction is fine. So let's try this last scenario here before we take a little break. So, because it's not really any different than what we've been doing. It's just one additional step. So let's go with a decomposition reaction where we have this silver sulfide decomposing into silver and into sulfide, or excuse me, sulfur compound. So here's our question. If we decompose 235 grams of Ag2S, how many grams of silver can we collect? All right, I want you to pause the video and see if you can set up this problem and solve it without me doing it. All right, I hope you have a number, and I hope that the number you have is 205 grams of silver. If this is the answer that you got, then give yourself a pat on the back and say, hooray, I'm a rock star, because you totally are a rock star. You're doing fabulously. If you did not get this answer, don't worry, you'll get it soon. You just might want a little bit more practice, so no problem. We'll go ahead and set this problem up. So we're going to start with the mass that we had, 235 grams of silver sulfide. Now, before we go any further, I just want to mention, if you have some problem on a quiz or an exam, and it says something about grams of one thing, and it's asking you about grams or moles of something else, and you don't know what to do, the best first step you can do is, if there are grams, convert them into moles. And if you don't know what else to do, you'll still get partial credit at that point. So we're going to take that step, we're going to convert grams to moles. So if you pull out your periodic table, you will figure out that 247.80 grams of Ag2S are how much 1 mole weighs. Now my balanced chemical equation says that 8 moles of Ag2S will make 16 moles of silver. And I just looked up the atomic mass of silver, so here it is, 107.87 grams of silver. And when we've done this setup, we can see that the grams of silver sulfide cancel out as units. The moles of silver sulfide cancel out as units. The moles of silver cancel out, and we are left with grams of silver. So we know we've done this setup right, and that this is the answer that we will get. All right, I think that's a great place for us to stop. In our next video, we'll do some discussion about percent yield, and then we'll also talk about some limiting reagent problems.